G'day, in this video we're going to be having a look at mass momentum and special relativity. This video covers dot point 7.4.3. We're now going to be looking at how the behaviour of light has an impact on matter. And in this video in particular, we're going to be focusing on how relativistic factors impact the momentum of a mass. So our key focus areas will be applying special relativity to mass and momentum, but also having a look at the consequences of maximum velocity for matter as well. So already we know that the Lorentz factor gamma, which is 1 on the square root of 1 minus v square on c square, is applied to all sorts of different physical measurements to account for relativistic factors which will warp them when an object is travelling near the speed of light. Today we're looking at momentum, and the formula here, PV, the momentum, in one frame of reference is equal to m naught v, the momentum in another frame of reference, divided by the square root of 1 minus v square on c square, or m naught v times gamma. So according to this equation, because momentum dilates, as the velocity of an object increases, the beta value increases, which makes the Lorentz factor increase as well. And by consequence, what that means is that there is a dilation in momentum similar to time. So for objects that are traveling really fast, approaching the speed of light, their relativistic momentum is quite different from how we would usually describe their momentum in a classical sense. I want to use this problem to highlight. So the question says that we have a neutron in the Hadron Collider traveling at 0.99 the speed of light, and we're being asked to calculate the classical and relativistic momentum of the neutron. So for the classical solution, we're going to be using the formula P equals mv. And for the relativistic solution, we're going to need to use our relativistically adjusted momentum. That is that PV is equal to m naught v on the square root of 1 minus v square on c square. To solve, we're going to need our mass for our neutron, which is 1.675 times 10 to the negative 27 kilograms. The velocity of the neutron, which is 0.99 times 3 times 10 to the 8 meters per second, which means that v square on c square can be written as 0.99 square. There's no rearranging needed for either solution, so let's substitute and see what we get. And so what we get is 4.97 times 10 to the negative 19 kilogram meter per second, as well as 3.53 times 10 to the negative 18 kilogram meter per second. And so these values don't seem particularly large until you divide one by the other and find that the relativistic momentum is 7 times more than the classical one. And if we were to make this neutron travel even faster, let's say it was 0.9999999 c, 7 nines, so extremely close to the speed of light, then we would find that the relativistic momentum is more like 2,236 times more than the classical momentum. Suffice to say, objects traveling near the speed of light have a much larger momentum than what classical physics would dictate. Why is that? Because as v approaches the speed of light, the gamma constant approaches infinity. Gamma gets larger and larger and larger and larger as we approach the speed of light until we hit this infinity point. And as the Lorentz factor approaches infinity, then the dilator momentum is going to approach infinity as well. Let's talk about this phenomenon in terms of energy. We know that kinetic energy is equal to half mv squared. So that's the momentum mv multiplied by the extra v, that's where the squared is, divided by 2 comes by multiplying by half. So we can rewrite as pv on 2. As a result, if we have a relativistic momentum approaching infinity, that would mean that the energy required to accelerate that object to that speed also approaches infinity. The consequence of this means that accelerating an object to the speed of light is Very, very, very difficult. More difficult than it would be based on a classical understanding of physics. Because the momentum that you would need to achieve is dilated due to relativity, meaning that the energy requirements are even greater. On top of that, it also suggests that the energy requirements to achieve the speed of light is infinite. Therefore, the speed of light is the speed limit for the entire universe. Nothing can physically travel faster than it. Thank you very much, everyone. In the next video, we're going to be looking at our last concept for this module, and that is Einstein's mass-energy equivalence, and may involve an equation that you have heard of before. But until then, have a good one.